reactants limit the amount of products a chemical reaction can produce. Let's use a simple example. Let's say we have 10 people in 5 chairs. If only one person can sit in a chair, then only 5 people can sit down at a time while 5 others stand. We can write this as a chemical equation. 1 person plus 1 chair equals 1 sitting person. So because it takes 1 person and 1 chair to produce 1 sitting person, then we know that with 5 chairs and 10 people, we are limited to producing at most 5 sitting people. So the number of chairs is the limiting reactant, or limiting reagent, in our example. But sometimes figuring out the limiting reactant is not very intuitive. And so we'll use the chair example to learn how to find the limiting reactant more systematically, by using mole ratios. If we want to analyze this problem using mole ratios, we start by looking at the coefficients in the balanced chemical equation. In the equation, the coefficients of person and chair are both 1, so the mole ratio between the reactants is 1:1. Now that we have the mole ratio between the reactants, we pick either one of the numbers that were given in the problem. We can pick either 5 chairs, or we can pick 10 people. It doesn't matter. Here, suppose we pick 10 people. We write this number into our mole ratio equation, and then put an x in the place of the number of chairs. Person divided by chair equals 1 divided by 1 equals 10 divided by x. If we solve the equation, we would find that x is equal to 10. And this represents how many chairs would be needed to have a perfectly balanced reaction with 10 people. So since we know from our problem that we only have 5 chairs, we now know that chairs must be our limiting reactant. We have fewer chairs than we need to react with every person. Let's say that instead of picking 10 people as our first number, we instead picked 5 chairs. In this case, we would write out the mole ratio with an unknown y in place of the number of people. Person divided by chair equals 1 divided by 1 equals y divided by 5. We can solve this equation in order to get y equals 5, meaning that we would need exactly 5 people to react with 5 chairs. However, we know that we actually have 10 people, meaning that the number of people is in excess. We have more people than chairs. Once again, this would make chairs the limiting reactant in this problem. We can also set this problem up by drawing a little table. Once we know our limiting reactant, drawing a table helps us figure out how much product we'll make. The columns of our table correspond to each part of our chemical reaction. Here, these are people, chairs, and sitting people. We label the rows with I for initial, C for change, and F for final. In the initial row, we put down all the values we start with, before the reaction takes place. So we write down numbers corresponding to 10 people, 5 chairs, and 0 sitting people. We just determined that chairs were our limiting reactant, and so all of the chairs get used up in the reaction. So in the change row, which is what happens during the reaction, we put a -5 in the column for chairs. These chairs reacted with 5 people, and so we also put a -5 in the column for people. Because our reaction produces 5 sitting people, we also put a +5 in the column for sitting people. The final row of our table, which is the value we end with, after the reaction takes place, we fill out by simply adding the 2 previous rows together within each column. So we're left with 5 people remaining, 0 chairs, and 5 sitting people. We have 0 chairs remaining because the chairs were the limiting reactant. Now let's do another example using an actual chemical reaction. Let's say we want to convert hydrogen and oxygen into water. We start with 10 moles of hydrogen and 7 moles of oxygen, and we want to determine how many moles of water are produced, and which reactant was our limiting reactant. We start by writing the balanced chemical equation for the production of water from hydrogen and oxygen. Next, let's write down the mole ratio for this balanced chemical reaction, using the coefficients of the 2 reactants on the left side of the chemical equation. H2 divided by O2 equals 2 divided by 1. Once again, we can pick either one of the 2 numbers that we are given in the problem. Let's say we pick the 10 moles of hydrogen. We put that in the numerator of our mole ratio equation, and then put an x for the number of moles of oxygen. We can solve this equation using cross multiplication, which tells us that 2 times x is equal to 1 times 10. Solving this equation tells us that x is equal to 5 moles of oxygen. This is the amount of oxygen needed to react with 10 moles of hydrogen. But from our problem statement, we know that we are given 7 moles of oxygen. Since 7 is greater than 5, we know that oxygen is the reagent in excess in this reaction. In other words, we have more oxygen than we need. This makes hydrogen our limiting reagent. Suppose we had instead picked the other number, 7 moles of oxygen, when we set up our equation. Writing down our equation, we would instead put our unknown variable y in place of hydrogen. We solve this equation again using cross multiplication, telling us that 1 times y is equal to 7 times 2. Solving for y tells us that y equals 14 moles of hydrogen. Since we know from our problem statement that we start out with only 10 moles of hydrogen, we can see that we have less hydrogen than we need to completely react with oxygen. So we once again find that hydrogen is our limiting reactant. Once you identify the limiting reactant, you can use the limiting reactant and the mole ratio to figure out how many moles of your product you'll make. Once again, the easiest way to do this is to draw an ICF table. The columns in our table this time will be hydrogen, oxygen, and water. In the first row, row I, we put down the starting conditions before our reaction takes place. 10 moles of hydrogen, 7 moles of oxygen, and 0 moles of water. In the second row, row C, we put down the changes that occurred during our reaction. Because we just found that hydrogen is our limiting reactant, and we'll use it all up in the reaction, we put a minus 10 in that row. Since the mole ratio of hydrogen to oxygen is 2 to 1, 10 moles of hydrogen will use up 5 moles of oxygen. So we put a minus 5 in the row for oxygen. Since the limiting reactant limits how much product we make, we look at the mole ratio of the limiting reactant to our product. Since the mole ratio of hydrogen to water is 2 to 2, 10 moles of hydrogen will make 10 moles of water. So we put a plus 10 in the row for water. In the third row, row F, we calculate the final number of moles of each chemical in the reaction. Adding everything together, we're left with 2 moles of leftover oxygen, 10 moles of water, and 0 moles of hydrogen remaining. Which makes sense because hydrogen is our limiting reagent. It's important to remember that once the limiting reactant is used up, the reaction will stop. We can visualize this concept by looking at a diagram of the atoms and molecules participating in our reaction. First, we can visualize the starting conditions for our reaction, which is a mixture of gaseous molecules of hydrogen and oxygen, which have not undergone any chemical reaction. We can count these molecules and see that we have 10 molecules of hydrogen and 7 molecules of oxygen. Next, we can look at our molecules again after the reaction has taken place. If we count again, we see that we have 10 molecules of water, 0 molecules of hydrogen, and 2 remaining molecules of oxygen. So our limiting reactant, hydrogen, got totally used up. But we do have some leftover oxygen. Let's do another limiting reactant example. Suppose we have some solid zinc, which reacts with aqueous silver nitrate. This reaction produces 2 products, solid silver and aqueous zinc nitrate. Suppose we start with 2.5 grams of zinc and 2.5 grams of silver nitrate, and we're asked to find the limiting reactant, as well as the amount of silver metal produced. First, we need to find the starting number of moles of zinc, and we do that by dividing the grams by the molar mass of zinc. We can look up the molar mass on the periodic table, and it's 65.38 grams per mole. So 2.50 grams divided by 65.38 grams per mole gives us 0.0382 moles of zinc. Next, we need to find the starting number of moles of silver nitrate. Again, we look it up, adding each element's molar mass together, and the total is 169.9 grams per mole. Using the same method, we see 2.50 grams divided by 169.9 grams per mole gives us 0.0147 moles of silver nitrate. Next, we write out our balanced chemical equation. Once again, we can start by writing down the mole ratio for this balanced chemical reaction, using the coefficients of the 2 reactants on the left side of this chemical reaction. Our next step is to pick either one of the 2 starting amounts of the reactants in our problem. Let's pick 0.0382 moles of zinc. We write down the mole ratio equation again, but we put an x in the place of the starting moles of silver nitrate. We can solve this equation for x using cross multiplication, which tells us that x equals 0.0764 moles of silver nitrate. This is the amount of silver nitrate needed to react with the zinc that we have. However, we know from our earlier calculations that we only start out with 0.0147 moles of silver nitrate. Since we have less silver nitrate than we need, silver nitrate is our limiting reactant. We're now ready to figure out the mass of silver that our reaction produces. Based on the chemical reaction equation, 2 moles of silver are produced for every 2 moles of silver nitrate consumed. Since silver nitrate is our limiting reactant, we know that all of it is consumed, all 0.0147 moles. And since the mole ratio is 2 to 2, that means that 0.0147 moles of silver must be produced by our reaction. To find the total mass of silver produced, we need to consult the periodic table again. The molar mass of silver is 107.9 grams per mole. We multiply 0.0147 moles by 107.87 grams per mole to find that 1.59 grams of silver are produced. 1.59 grams of silver is the theoretical yield of our reaction. In other words, it's the yield of product that would be produced if the reaction proceeds perfectly. However, in many real-world cases, the reaction produces less product than the theoretical yield. For example, suppose that we performed our reaction in a laboratory, and we only measured an output of 1.00 grams of silver. We could call this number the actual yield of our reaction. Now we can calculate the percent yield in order to measure the overall efficiency of our laboratory process. We simply divide the actual yield by the theoretical yield and then multiply the result by 100. So 1.00 divided by 1.59 times 100 gives a percent yield of 62.9%. If we want to produce silver from silver nitrate with higher efficiency, then we'd want to get the percent yield as close to 100% as possible. Alright, as a quick recap. Limiting reactants limit the amount of products that are created in a chemical reaction. During a reaction, theoretically the entire quantity of limiting reagent is consumed, determining the final amount of product and thus the theoretical yield. However, in real-world applications, the actual yield of a reaction is lower than the theoretical yield. We can measure the efficiency of a reaction using the percent yield, which compares the actual yield to the theoretical yield.